Traditional outdoor agriculture produces approximately 500 grams of saffron per hectare. However, in an optimized indoor vertical environment, that yield increases to a 1,500-gram equivalent. Outdoor production is limited by environmental volatility and the heavy manual labor required to harvest across expansive, arid fields. Moving indoors also increases the concentration of the plant's essential phytochemicals. Controlled environment systems allow growers to optimize levels of Crocin, Safranal, and Picrocrocin, the compounds that define the stigma's pharmaceutical value. Unlocking this 3x multiplier requires moving past standard CEA protocols like static photoperiods. Saffron operates on a distinct biological schedule where reproductive growth follows a sequence unlike most crops. To reach biological limits, the plant must be managed as a system of stage-gated atmospheric demands, where every input is tuned to a specific metabolic transition. This cultivation strategy is built on the concept of reverse phenology. In this cycle, reproductive flowering occurs before or sometimes simultaneously with vegetative leaf expansion. To align HVAC and CO2 systems with this timeline, we must build a chronological roadmap that accounts for these unconventional growth stages. Precisely mapping temperature, light, and CO2 to this reverse timeline is the only way to engineer the phytochemical quality of stigmas in a controlled setting. The crop cycle begins during the hottest summer months, from July through September. During this phase, corms are kept in dark chambers suspended on racks at a constant temperature of 25 degrees Celsius. At this point, the plant is in true dormancy. The corm is not actively transpiring or photosynthesizing. Because the plant is dormant, CO2 and humidity parameters must remain at baseline levels. Standard indoor climate automation should not be used to drive humidity or carbon during this period, as excess moisture will induce rot. Forcing atmospheric resources during summer dormancy wastes facility energy and can destroy the crop's yield potential before the first sprout appears. In October, the focus shifts from photoperiodism to thermoperiodism to break dormancy. The temperature is dropped sharply from 25 degrees down to 13 degrees Celsius. Following this cold shock, the environment is stabilized between 14 and 17 degrees to support optimal flower development. This temperature shift must coincide with a specific light recipe, 1000 lux provided by a 50-50 combination of red and blue LED spectra. These specific wavebands are required for saffron photomorphogenesis, providing the light quality necessary for floral induction. CO2 emitters are activated the moment flower spikes and the first true leaves emerge. The CO2 concentration is increased to 700 parts per million to maximize floral biomass during this critical window. This convergence, the 13-degree shock, binary CO2 activation, and monochromatic light, drives the biochemical pathways for Safranal and Picrocrocin accumulation. Once the rapid 2-week flowering harvest is complete, the focus shifts from the flowers to the long-term health of the corms. From November through May, the leaves remain green in a cooled environment. This is the vegetative phase. During these months, the plant's development is governed by source-sink dynamics. The green leaves act as the source. As they reach their maximum leaf area index, they actively absorb atmospheric carbon. This carbon is used to construct new daughter corms, the sinks, which replace the dying mother corm. Maintaining CO2 at 700 parts per million is necessary to support this continuous carbohydrate transfer. Systemic failure occurs if CO2 is shut off prematurely after flower harvest, as the new corms rely entirely on spring photosynthesis. Supporting the vegetative canopy with CO2 through the spring ensures the multiplication of robust corms, securing the yield for the following year. The completed grow chart reveals a binary structure, a period of high-temperature dormancy with no inputs, followed by an immediate shift to a cooled environment with high CO2 and targeted light. This model is distinct from standard CEA crops like lettuce or cannabis, which require constant year-round atmospheric support. Dosing for saffron is strictly stage-gated, activating only at the 13-degree cold shock, and sustaining only while the vegetative canopy is present. Executing this environmental precision flawlessly ensures a high-volume, consistent yield of pharmaceutical-grade saffron. Adopting this reverse phenology approach changes the unit economics of the crop, making indoor cultivation a viable method for large-scale production. Mastering the specific requirements of Crocus sativus transitions indoor farming from simple spice cultivation into high-yield phytochemical engineering.